Welcome to homework.
Okay, we need to calculate a reduced mass for HBr. And we've been told that H, or proton, weighs 1 gram per mole, and the bromine, 79, weighs 79 grams per mole. Now, the formula for reduced mass is simply going to be product of the two masses, so 1 gram per mole times 79 grams per mole divided by the sum of the two masses, so 1 gram per mole plus 79 grams per mole. And what's nice is that the units will give us grams per mole, right? Because we'll have the sum on the bottom, it'll have grams per mole, and the top will be grams per mole squared. Grams per mole squared over grams per mole is simply grams per mole. Either way, we're going to get the number 79 divided by 80. So 79 divided by 80 equals 0.9875. 0.98. Give yourself some room. 75 grams per mole. That is our reduced mass for HBr. Now we've got to calculate the vibrational frequency. What we need for the vibrational frequency is V equals the square root of, and it will be K, the force constant, over the reduced mass. Great. Now, the way the units work out for that is that force constant is in newtons per meter, and that's going to be also divided by mass. For example, we get kilograms. Okay, and so we know newtons are kilogram meters per second squared. Right, so if we have kilogram meters seconds inverse squared over kilograms, and then we've got, it's newtons over meters, so we've got a meters down here. Kilograms, the meters will cancel, and we left with the square root of seconds inverse, which is equivalent to seconds inverse. So the units match out so long as we use kilograms for the mass. Now, in our case here, we've got grams per mole. We're interested in just a single molecule of HBr when it comes to the vibrational frequency. So we'll need to convert our reduced mass in terms of grams per mole into kilograms. Now, the way we do that is we take this 0.9875 grams per mole, and if we want kilograms, we've got to go, there's 1,000 grams. Sorry, we need to get rid of grams, so that needs to be in the denominator. There is 1 kilogram in 1,000 grams, and we're not interested in a mole, we're interested in a single molecule. So we know that there is 6.022 times 10 to the 20. Oh, we need that. There, we need moles on top again. I'm getting all this backwards. Apologies. We know that there is 1 mole in 6.022 times 10 to the 23rd molecules. Right, so this will give us per molecule when we finish this computation. So that's going to be, let me compute this off to the side. And the final answer I get is 1.6398 times 10 to the negative 27 kilograms. All right. So that is our reduced mass in the units that we need it to be, such that they will cancel with our newtons per meter. Great. Now we need to just input our information. We know we need the square root of k over reduced mass, which is equal to the square root of, let's see, they told us 384 newtons per meter. And our reduced mass is in 1.6398 times 10 to the negative 27 kilograms. And if we calculate this off to the side, give me just a second here, we are going to get 4.8392 times 10 to the 14th seconds inverse. And that's a pretty reasonable answer if we, for example, just look up on Google what the vibrational frequency of HBR is. Their answer is the literature value is 7.68 times 10 to the 13 hertz. Hertz is the same as seconds inverse. So we're in the ballpark of the literature recorded value, just in terms of a little bit of sense making. We've got maybe 5 times larger than the literature value, which could be for various reasons, but the math checks out in either case.